Hello and welcome to Task Shaded Chopper. In this task, we are finally doing our own lighting calculations. We are doing this by using Phong shading model, specifically the GoRAD and Phong lighting models. The difference between GoRAD and Phong is that for the GoRAD, we are doing calculations for each vertex, but for Phong, we are doing for each fragment that we see. So the difference is that the GoRAD calculations are in a vertex shader and Phong calculations are in the fragment shader. The basic overview of the lighting model is given in the task description. As you can see, there is a list of variables and also how to get them, and also the visualizations about the dot product and how the light source and viewer position are related to each other. But let me show you on the whiteboard what the Phong lighting model actually is. So as you can remember from the lecture, the Phong lighting model consists of three main components. The first component is the ambient component, which has the material's ambient color and also the light color for the ambient light. Then we have the diffuse lighting, so the diffuse color of the material and also the diffuse color of the light. But also this term is influenced by the angle of the light. We can visualize it by having a surface that we want to light, and then we imagine a unit of light landing on this surface. So by the unit of light, I mean that the light beam has a certain width, so x in this example. And if we put this beam at an angle, but the beam width is the same, we see that the area that the beam lands on is larger than it would be if the angle is 90 degrees. So that means that the light is spread in the angled case more, which in turn makes the surface dimmer. So how do we calculate this? So we have a normal vector, and then we also have the direction to the light source, so L. And we want the cosine of this angle between them. And we can get it easily by just using a dot product, so normal times light direction. The third term is the specular highlight. This also has a different color for the material and the color, but this will be influenced by the direction of the viewer and also the reflected vector of the light. So if we have the surface and our camera is here, then we have this vector going to from camera to the surface or from the surface to the camera. So when would the specular highlight occur? It would occur only if the light is reflecting straight to the camera. So if we have a normal vector here, as we do, then the light should come from this direction, L, and it will be reflected by the normal vector, and that would be R. And the more similar the V and R are, the greater the specular highlight is. So we want the cosine of this alpha. So VR, but also we want the highlights to be in a small spot. So to exaggerate the specular highlights, we should put it to the power of S, which is a shininess. So the more shiny the material is, the sharper the specular highlight is. In practice, the ambient and diffuse materials are usually the same, so we consolidate them into one single variable. Then we can put the light colors inside the brackets. And usually the material color for the specular highlight and the light's color is white, so we can just leave them out. They can be just constant one. So we can write this as a specular term. And that will be the implementation of our Phong model in this task. So if you look at the code, it consists of 6 files. We have our HTML file, which stays the same as our other tasks. Then we have our JavaScript file that will be implementing some code here. And then we have 4 different shaders. So we have We have the vertex shaders for the go-route and the Fonk models, and then we also have fragment shaders for both of them. And in our task, we have to rotate between the two to see the difference. But I will show you the implementation of the go-route in this video. The Fonk itself has to be implemented independently. So let's look at the JavaScript code in more detail. Let's start from the top. We have the basic things renderer, see in camera. We also have the variable for the chopper. And then we have vertex shader and fragment shader variables, as we did in previous task. But now we also have four different variables for the go-route and Fonk shaders as well. So if you remember, we have to rotate between the two. So the vertex shader and fragment shader are the current shaders, and those are the ones that we load from the disk. Then we have the status container and shader mode. If we activate the code now, we see that it's empty space, but we have this text here, which indicates that we are seeing go-route shader at the moment. And that's the contents of the status container. Then we have the light position and light trajectory. So light position is obviously the light position where it is in the world space. Then we have the light trajectory, which is the path that the light travels. So in this task, the light is moving around, so we can see how the light's position changes the shading and the specular highlight and color of the chopper. Then we have the viewer position in the world space. That's at the 008 coordinate. Then we have our millis and rad. And in the onload function, we do the exact same things as previously, but now we load two different shaders. We are using the perspective camera as in previous tasks. And then we have the change shader function, which changes the shader mode. So it's either 1 or 0. And if it's 0, then it's go-route. When it's 1, then it's Fonk. We also have the light trajectory. We have defined it as a cut-mull-rom curve, which is a spline. We are looking at splines in Basic 2 module, but this is a smooth curve in a 3D space that the light will follow. Then we also have the event listener here for the right arrow and left arrow. That will change the shader from Fonk to go-route or from go-route to Fonk. In the change shader, we also traverse the objects in our scene. And this is because we need to change all the current shaders from one mode to another. And we also see that we set the needs update to true. So it will actually upload the new information to the GPU, and we can see the difference. In the draw function, we update the light position according to the trajectory, and we also update the light position value in the shaders. We also see here that we are applying the camera's world inverse matrix, which transforms the light's position into a camera space. Here we also handle the rotation of the blades. Hopefully you have been doing something like this. Then we also have our regular function add hanger, add chopper, add wall, and create cube. And this time the chopper is a sphere. So we also have a create sphere. If you want a smoother sphere, you can change the variables here. It will make the sphere more smooth. It might become so smooth that the difference between go-route and Fonk lighting models becomes indistinguishable. And then we also have the function create shader material. Here we have to add two uniforms to our materials. First we have to add the light position, which is a vector 3 object, and then we have to add a color, which is a vector 3, but in 3JS we have to specify that it's a color, because it will convert it from the byte vector to linear vector. So to create a uniform, we first define it by a name. That will be the name that is same in the shader, but also it will be used to access it in the JavaScript code. Then we expand it into a structure, and first we have to specify what type it is. So this is a vector 3 type, so here we have a v3. We use this v3 here. And the value itself, Doesn't really matter what you put right now because it will be updated every frame. But we can just use our global variable light position. And the same for the color. So here we put the type as a color or C, and the value is the argument of this function, so color. And now we have a chopper in our browser. The rest of the Corout implementation is in the Vertex Corout.glsl, so this is the Vertex shader for the Corout. There is no implementation in the fragment shader, so the fragment shader stays the same. But let's see what we have to do. So let's start from the first point, calculate the vertex position in the camera space. So camera space, if you remember, is the space that is transformed from the word space, and we get the word space from the local space. And we have the position given by the 3GS, which is in local space, so that we have to convert it into word space, and from there to the camera space. This matrix has already been used in previous tasks, so that's the model view matrix. We have to store the position in the vector3 object, but if you remember correctly, the model view matrix is a 4x4 matrix, so we have to convert this position into a homogeneous coordinate system, and then the result should be taken like x, y, z. The next thing we have to do is calculate the correct normal in the camera space. So a naive solution would be to use the same matrix, the model view matrix, but this does not actually work because the model view matrix also has the translation, and we don't want to translate normals because then the normal will not be perpendicular to the surface of the mesh. So what we have to do is we have to use a separate matrix, a normal matrix, which is inverse transpose of a model view matrix, and this keeps the normal in perpendicular to the surface. So what we have to do is use the normal matrix and multiply with normal. But this might still not be correct because it might not be normalized. The matrix keeps it perpendicular, but it might change the size of the matrix, so we have to normalize it as well. Next, we have to find the direction towards the viewer, and then we have to normalize it. First thing to note here is that we want to do all our lighting calculations in camera space, and we know, therefore, that the viewer's position is at 0, 0, 0. So we can actually save it into our variable. But now we have to find the direction towards the viewer from the vertex. And we have already calculated the vertex position inside P. So we can just do difference between points to get the vector. So that's the direction towards viewer. That's the V vector. And then we have to also normalize it. It's the same for the light source, but instead of using the viewer position, we use the uniform light position. So we can copy it. So that's in the L, and we use the light position instead of viewer position, and then normalize it. One more thing we have to calculate is the reflected vector. So for that, we have to use the reflect function of the GLSL. If we look at the documentation of this function, we see that it takes in two vectors. It takes in I and N. I is the incident vector, so that's the vector from the light to the vertex, and this N is the normal vector. In the description, we also see what formula it uses behind the doors. So that's the I minus 2 times the dot product between the normal and the incidence vector, and then we multiply it with the normal vector. So that's vector 3 and the R for the reflect, and then we use the reflect. And the first argument will be the direction from the light, so that's the minus L, because the L is the direction towards the light, so we want the opposite. And then the second argument will be normal, so that will be the N. And it seems like nothing broke, so now we have to put it all together in the interpolated color output. So first let's define the diffuse color and also the ambient color. The materials color is the color itself. So color, and then we multiply it with the combination of the ambient and diffuse color. So for the ambient, let's leave the ambient empty for now, so it will be 0. But for the diffuse, we wanted the dot product between the normal vector and the direction towards the light. So let's see. In the output, now everything is shaded. And we have light here, we have a dark color here. But the dark color might be too dark, so let's add the ambient color, might be like 0.1 maybe. So it's less harsh. One other thing to note here is that the dot product might be negative. So, but we want it to be always positive. So we have to use the max function and floor it, clamp it at 0. So now the negative values will not cancel out the ambient component, and it looks cool. Note that the ambient color might as well be a vector. So for example, let's say that we want the ambient color to be greenish, a bit yellow, so 0.5, 1.0, and 0.0, and then everything looks very green and a bit yellowish. Let's make it a bit less harsh, so might be 0.2, and this might be 0.05, and then still has this faint tint of green to everything. But for now, let's leave it at 0.1, so it has a white ambient color. So I saved our current progress into this ambient diffuse variable, so we can add our final term here, which will be the specular highlight. And as we saw, the specular highlight is just the dot product between the reflected light direction and the direction towards the viewer. So let's write the dot product between the V and R. And if we just save, we see that it looks strange. Everything is black, and then every other thing is white. So let's add the power to our equation for the shininess, and let first it be 10. Well, it still looks strange. So what the problem now is that the dot product here, as with the other dot product, can be negative. So we have to do exactly the same thing. We have to take the maximum between 0 and the dot product. So after doing it, everything looks good, but now we also see this very, very white patch here, and that's the specular highlight. So now I have also separated the specular highlight into a separate variable. You could do exactly the same thing for the ambient and diffuse as well. So for the ambient, we can just create a variable ambient and then color times 0.1. And for the diffuse, we do the same thing as in here, but take the ambient out, so color times this term. And we can combine them in this variable. And the result looks exactly the same. So all three terms are in a separate variable, and then we can add them here together. You can experiment around with this. You can change the color of the ambient light, or you can change the diffuse light color. The floor is yours. You can also change the shininess. For example, let's change it from 10 to 50. The change has not been very great, but for 250, then the specular highlight is very sharp, but also you can't see it all the time. And that actually is related to the question here, which is that why is Gouraud missing a specular highlight on the back wall? So if you are implementing the Func model here, you will see the specular highlights on the back wall. And the question is why can you see it for the Func and why can't you see it for a Gouraud? And this is related to the result here, and why the specular highlight is sometimes seen and sometimes not. So your task is to implement the Func variant of this lighting model, and this has to be done with the vertex Func GLSL file, where you have to complete this vertex shader, and also you have to complete this fragment shader. Finally, after you have answered this question, then your task is done. So good luck for solving.